Hello, students. This is our lecture on Newton's third law of motion. So Newton came up with really three laws of motion. We've covered two of them so far, and let's just review quickly what those are. Newton's first law of motion is an object's state of motion will remain the same unless acted upon by a net force. Another way of stating that is to say an object at rest tends to remain at rest. An object in motion tends to remain in motion unless acted upon by another force. Now, it's really easy to understand intuitively why an object that is resting doesn't start moving, right? That intuitively makes sense to us. A ball sitting on a table will remain motionless, or a ball sitting on the ground. A ball sitting on the ground will remain motionless unless acted on by a net force. Now, the forces right now are equal, right? The force of the ball is pushing down on the ground, and the force of the ground is pushing up on the ball, right? And those forces are the same. A ball moving, right, would continue to move. If a player came up and kicked the ball, right, that ball would then continue to move indefinitely unless acted upon by other forces, and we know that those other forces are friction and gravity, and that would slow those things down. That's why the ball eventually comes to a stop. Why isn't it that objects, so if objects in motion tend to remain in motion, why don't they remain in motion permanently? Why don't, if I throw a ball, it just travels forever and ever and ever? Well, because we have forces that are acting against that acceleration. We have the force of friction, fluid friction of the ball through the air, and then, of course, the force of gravity. Newton's second law of motion is force is mass times acceleration. How much force something exerts is its mass times acceleration. We measure mass in kilograms. We measure acceleration in meters per second squared. So, and we call that for shorthand a Newton. So force equals mass times acceleration. That's Newton's first two laws. Newton's third law. What is Newton's third law? All right, so we'll preview the ideas. I'll kind of skip past the bell ringer, but then we'll talk about action and reaction forces, and then we'll quickly get into momentum a little bit and just specifically define momentum. All right, so Newton's third law. You may have heard this before. It's famously known as, for every action, there's an equal and opposite reaction. All right, so key ideas, just to consider. What happens when an object exerts a force on another object? How do you calculate the momentum of an object? What exactly is momentum? And what is the total momentum, right, after objects collide? All right, so let's just go over the questions quick, just something to consider. You've learned that forces account for changes in the motion of object, right? Using what you have learned, explain what happens in the following situation. All right, so an ice skater holding a basketball is standing on the surface of a frozen pond, right? The ice skater throws the ball forward, and at the same time, she's going to slide in the opposite direction. That's far more likely to occur if you're on ice and not if you're standing on the ground. And why is that the case? All right, so is the force of the ball greater than, less than, or equal to the force of the skater? And explain your answer. Right? I will tell you that the forces are going to be the same. Is the acceleration of the ball greater than, less than, or equal to the acceleration of the skater? Right? Remember Newton's second law, F equals ma. Force is mass times acceleration. So before you answer that question, you want to consider which of these has a greater mass, right? Which of these has a greater mass? And then if the forces are the same, right? Because they are, the forces are the same, right? And we're calculating for acceleration, right? So remember our famous equation. Oh, it might be super hard to see. I'm going to go way forward to the camera there. Oops, sorry. F equals ma. So there's our equation. F equals ma, force equals mass times acceleration. Well, if we're trying to figure out acceleration, we know that's the force divided by the mass. It's the force divided by the mass. Well, if the forces are the same, right? The forces are the same. but we know that the mass of the person is significantly greater than the mass of the ball. So we have a bigger number going into this number. That's going to make our answer smaller. If we have a smaller number going into a bigger number, that's going to make our answer bigger. Right, so the acceleration of the ball is going to be greater because the mass of the person is less. Yeah, math. All right, so action and reaction forces. What exactly is Newton's third law? All right, so when an object exerts a force on another object, right, the second object exerts a force equal in size and opposite in the direction of that first object. All right, so this is Newton's third law. All right, so back to our example of a player running up and kicking the ball, right? So a player runs up and she kicks the ball. The ball is actually exerting a force back on the player's foot, right? And the player's foot is exerting an equal force on the ball. Now this can often be confused with, why does the ball then move? Because if the force of the ball pushing back on the foot is the same as the force of the foot being applied to the ball, why would any of them move? And we'll get to that in just a second. But those forces are indeed the same, right? So the ball, so let's say here's the ball, and the player kicks the ball this way. Well, the magnitude of the force of the ball is going this way, and the magnitude of the force of the foot is going this way, and they are the same. For every action, there's an equal and opposite reaction. We'll get to a little bit later why it is that the ball actually moves. All right, so action and reaction forces. Forces always occur in pairs, right? So there's never a force that's isolated. You can't have a force acting and not have another force be involved, right? So for every action force, there's an equal and opposite reaction force, right? But forces in a force pair do not act on the same object. All right, so another way of saying that is, let's go back to our player kicking the ball. The ball exerts a force on the foot, and the foot exerts a force on the ball. Right, so they're different forces acting on different objects. Equal forces don't always have equal effects, right? And this gets back to our concept of why the ball moves. Right, so let's think about gravity. Right, for example, the action force of Earth pulling on an object and causing it to fall is much more obvious than the equal and opposite reaction force of the falling object pulling on the Earth. Yep, falling objects are pulling on the Earth, right? Because again, remember, gravity. We define gravity as the force of attraction between any two objects, right? But the strength of the gravity is dependent upon the mass of the object. The strength of the gravity is dependent upon the mass of the object. So, if you were to stand and hold a bowling ball and drop that bowling ball, not only does the ball accelerate towards the Earth, but yes, in the strictest sense, the Earth accelerates towards the ball. But why don't we feel that? Wait a minute, what have you been smoking? You're trying to tell me that when I drop a ball, that the Earth actually accelerates towards the ball? And the answer to that is yes, but it's obviously negligible. It's absolutely negligible. Again, let's go back to our equation. Let's go back to force equals mass times acceleration. Back to our force equals mass times acceleration. This was one of these sample problems we did the other day in class. Remember our acceleration equation? So if we rearrange this algebraically, our acceleration equation is force divided by mass. Okay, so the force of the ball, 9.8 meters per second squared, divided by the mass of the ball, the force of the ball in newtons, so kilograms, divided by the mass of the ball, right, will give us our acceleration, right, in meters per second squared, right? So we take the force being exerted upon the ball, and we divide that by the mass of the ball, which is only 5 kilograms. Well, it's the same force being exerted It's the force of gravity. So it's the same force of gravity being exerted upon the Earth, right? But that force then, what's the acceleration of the Earth? We have to divide that force by the mass of the Earth, which of course is a giant, it's a massive number. So this acceleration gets super, super, super tall, super, super, super small, right? If this seems at all confusing, after you're done with this lecture, watch one of the follow-up videos that'll help explain that. All right, so again, here's just these equal and opposite reaction forces. The video doesn't play, but if I take a hammer and I hammer it against the nail, right? The hammer exerts a force on the nail, and the nail exerts a force on the hammer, which is why the hammer will stop right about here, an equal and opposite force. So the hammer stops, right? Now, why does the nail then move into the wood? Well, now we have so the hammer hitting the nail is one system. A separate system is the nail and the wood, right? And the nail exerts a force on the wood, and the wood exerts a force on the nail. But because they're different masses, one accelerates more than the other. All right, so for every action, there's equal and opposite reaction. Very quickly, let's just talk about momentum. We're not going to do any calculations of momentum for the exam, but I just want to walk through it quick. What exactly is momentum? Momentum is just defined as that it's that property of mass when it's moving. So P is momentum, and momentum is mass times its velocity. Mass times its velocity. Not its acceleration, but its velocity. And remember, velocity is just speed with a direction, right? So velocity has one unit of time, right? Meters per second. Acceleration is change in velocity. Acceleration is change in velocity. So just reviewing those two concepts. For a movement along a straight line, momentum is calculated by multiplying an object's mass and its velocity. So essentially, it's speed with a direction. Excuse me. Here's the definition. It's the quantity defined as the product of the mass and the velocity of an object. The SI units of momentum is kilograms times meters per second. Again, notice there's only one unit of time. Remember, velocity is essentially just speed with a direction, right? But when we're doing the calculations of momentum, we just figure in the mass and then the speed, not the direction. Right? Momentum and velocity are the same in the same direction. Momentum increases as mass and velocity increase. Now again, this intuitively makes sense, right? This intuitively makes sense. If I throw a beach ball and you catch a beach ball, that beach ball is not going to have a lot of momentum because it doesn't have a lot of mass. But if I take a bowling ball and I throw it at you, that bowling ball is going to have a lot more momentum. Why does it have a lot more momentum? Because the mass of the bowling ball is so much greater. So here it comes back to this idea of force. Intuitively, we understand this. Force is related to the change in momentum. As the period of time of the momentum's change becomes longer, the force needed to cause the change in the momentum becomes smaller. All right, we're not going to worry too much about calculating. This is just getting into just defining what momentum is just a little bit. The big takeaway is this, is going back to this idea that for every action force, there's an equal and opposite reaction force, and that's Newton's third law. Now again, let's take an example of pulling a rope. No, that's not a good example. A horse pulling a cart, right? A horse pulling a cart. All right, so imagine a horse harnessed up to an old wagon, right? 1800s. Right, so the horse is exerting a force on the cart, and the cart is exerting an equal and opposite force in the opposite direction on the horse. Why then does the cart move? Well, the cart moves because the horse is also exerting a force on the ground. So the horse is pushing the ground backward. right? The horse is exerting a force on the ground backward, and the ground is exerting a force on the horse forward, right? And the force being exerted on the horse forward, right, is greater, right, is greater than the force being exerted on the horse backward by the wagon. And that's why the wagon moves. Now, I know that can be confusing, but in the end, the big picture is just this. For every action of force, there's an equal and opposite reaction. All right. Follow up your understanding of this by reading section 12.3 if you haven't done so. That's pages 412 to 417. The textbook PDFs can be found in Schoology. Also, supplement your understanding by watching one of the several videos on Newton's third law on the resources page, title or in the resources folder, the learning resources folder, and it's titled Newton's third law YouTube clips. All right, thanks. I hope that was helpful.